Hello everyone. Welcome to week 6 of the interactive session. So I was not available last week, so that is why this will be the week 6th session. And tomorrow from 3 to 5, I will be taking another session to make up for the lost session. So today we will mostly discuss about the part about traders, and tomorrow we'll get into the part about bias variance trade-off and generalization and so on. So let us wait for a few minutes so that few more people join.
Good
Okay.
afternoon, sir.
Hi, good afternoon.
So today is this for week 7 or week 6, or we can ask anything.
So you can ask anything, but
Okay, okay.
because I missed last week, so
Oh, okay, okay.
uh, yeah, but
Sure.
yeah, you're free to ask other
Okay, okay.
questions if
Yeah, yeah.
there's nothing. So I guess you can start. Not many people are joining. So yes, so if you have any questions regarding, say, the autoencoders PCA or even for bias variance trade-off, we can discuss those questions or any doubts regarding any problems there.
Sir, I would like to, this week 7 is more fresh in my mind right now. So
Okay, okay, sure.
it's becoming really overwhelming.
Oh,
Previously, what was that? I have to forgotten.
okay, okay,
Mm.
okay.
So I'll start backward. Just I'll say the difference between ensemble and dropout.
Okay.
So is it the? I mean, you can add later on. As
Mhm.
per my understanding, in dropout also, we are taking an average of the networks, all the sub networks.
So in dropout, what we do is with some probability we say that this neuron is not active for this run.
Yeah, we have
Huh.
different networks. I mean, so many different networks are possible,
Right.
right?
Yes.
and we are taking for the output we are we are taking the weights, we are assigning the weights, not for the output, sorry, for the testing, the last stage. We are not
Yes.
going through all of these networks,
Mm.
but we take only one network, the full network, not the sub network,
Yes.
and we assign the weights uh, based on the probability of the neuron. If that neuron was
If it was trained
include,
or not.
yeah,
Mm.
with the probability, then the accordingly the weight also is scaled like
Yes.
accordingly.
Yes.
So the is the difference between dropout and ensemble. I mean, dropout uses ensemble, but in ensemble we don't have this p probability weights, right?
Okay. So okay. So
Yeah, you
dropout.
can start from beginning. This
Yeah.
was
Yeah. Yeah.
like
Sure.
kind of what I understood. Yeah, you can continue.
Okay. So dropout is a form of ensemble, you can say, because
Okay.
what we do is on in ensemble methods is we have different models, let us say, and we train our each model. We train each model independently, and we take the average or combined
Hmm.
output of all of these models so that your variance is reduced, so that you have more information from different models instead of just relying on the output of a single model.
Hmm.
Now,
Hmm.
dropout can also be considered to be a form of ensemble learning. Why?
Okay.
Because suppose you have some input X,
Hmm.
and according to some dropout probabilities, you train the model, right? So
Hmm.
now you are training your model on a some sub network, let us say,
Hmm.
and in a different epoch, because these dropouts are basically probabilities, you will
Hmm.
train on a different sub network. So across 2 or 3 epochs, you are training on 2 or 3 different sub networks. So that means you are training on 2 or 3 different sub models, and
Okay.
then that really is in essence that is ensemble learning, because you are training your 2 or 3 different models and taking the output, uh, or combining the output of all of these. So dropout can be considered as a type of ensemble learning.
Okay. Yeah.
So
Thank you.
that is the basic idea, huh?
And this bias variance, apart from the formula, not
Hmm.
able to understand uh, uh, what it, I mean. They say that bias is like how far and from the actual, and
Yes.
variance is like how different from. Not able
Hmm.
to understand. I tried to read and all. It was more same things were written again and again, but I
Okay.
was not able to follow.
Okay, so let me join. Give me 2 minutes. So bias and variance. Okay. So my screen is visible, right?
No,
No. Uh,
I don't know if it is visible for, or it is visible for others.
others, can you confirm if my screen is visible or not? Arijit, Mahesh, anyone?
Not visible.
Not visible. Oh, how about now? Is my
No,
screen visible?
no, no.
Oh, can you reconnect because I think Manikantan is saying it's visible.
Oh, okay, okay. I'll leave and connect them. Yeah, it is visible now.
Okay, great. Okay, so when we're talking about bias variance, so what we want to say is that how well has your model been trained? So because we know what is, suppose we know what is a true function, and
Mm,
now your aim is to say how well is your model or how well is the function that you have learned close to the true function. And so
okay,
that captures the notion of bias. So bias is basically given the training data that you have, how well have you learned the underlying function, the true function. And bias, sorry, and variance basically says uh, if I change my output a bit, should will my or if I change my inputs a bit, will my outputs will also change? How much variance will there be if we change the input or if we change the data points? So
okay.
so when we talk about bias, so suppose I know that uh, my points are something like this. I have a point something like this. Something like this. Right? And now, suppose I learned two different models. So say my model one is something like this. This is my model one. So that is my, that is, I have learned this model one using some algorithm. And this is my, yeah, this is a learned model,
Simple algorithm.
some simple algorithm. And suppose I learn another model, which is say something like this, something like this. This is model 2. So here, which one do you think is a, so this is a true model. Which one do you think is the is truly
More
approximates
closer
the
to,
true function?
yeah, model 2.
Yeah, model 2, right? So this
Mm,
is a true model. So model 2 is better. It better approximates the true model than model 1. So then we say that model 2 has a low bias. By bias we mean, so how do you quantify, how do you say that something is better than uh, something is good or something is bad? That is, we say that the loss or the training loss
mm-hmm.
for model 2 is less than for model 1. So that means we say that model 2 has low bias with respect to the true model. So bias basically captures this notion that how much farther you are from the true function. Now, when we talk about variance, so this is bias. Hopefully, this is clear.
Yeah, yeah.
Okay. So now, when we talk about variance, if we take the same example, so okay, so when we're talking about bias, we're talking about the training loss. So that is
Mm-hmm.
important. And whenever talking about variance, so suppose I have the same data points. I have this, and okay, let this be my true model. Okay, and now suppose I have learned a model which is something like this black one, and so on. Now, suppose I have a test. So suppose I put a test point. Suppose I put a test point here. So this is my test point. Now you see, instead of this black, or let us say this black is some model 3 that I have, and I have another function that looks something like, say something like this. So that this is M4. Now I want to check what is the loss for the test point with respect to M3 and what is the loss with respect to M4. So for which case do you think the test loss will be higher?
M3.
M3 will be higher. So the test loss for M3 will be higher. So why that happens is because when we are learning the model M3, we are almost memorizing all of the data that we have. We are trying to fit over all of the data that we have. Right? So these are the data points that we had. So during test time, if we have a new data point, which are not these data point, so that means the function will not be able to generalize to this point, or it will not be able to, let us say, find a good score, give a good error for this point. So that means it is overfitting to the points that you already have.
M3 model, yeah.
Yes, but it will not be able to generalize to a newer point. But that does not happen for M4 because it is not overfitting to all of the points. But again, it has a good error over all of the remaining points. So for M3, we can say that uh, so model M3 has a high variance. So one way to understand this is something like this. Suppose you are preparing for an exam, and if you just memorize all of the questions in some book, and during the examination some other question comes, it is possible that if you memorize everything, you will not be able to answer a new question. So that means you're overfitting your knowledge to the book that you have read, but not to the overall concept of the problem. So overfitting is something like this. You memorize everything that you see, but you will not be able to do much when a new data point arrives or some new unseen point or unseen problem arrives. So that means it has high variance. Why it has high variance? Uh, because this data has it overfits to the data, and once you get a new point, it will have a high test loss in that case. So that is what is known as high variance. And so again, once we talk about variance, we naturally we get to high variance implies that we have overfitting, and we don't want our models to overfit. And if we have high bias means high training loss. That means we are not able to train properly. So that means we have underfitting. So those are the concepts of bias and variance.
Oh, thank you.
Okay, any other question?
For this week, if more questions on other topics also, if we could
Yeah,
get
sure. Yeah, sure.
for week 7. I mean, the quiz covers little, but to
Mm-hmm.
be able to whether we understood or not, if there are more some simple concept questions, if there are,
Okay. Yeah.
yeah, that would be.
Mhm.
Oh, because that is only there were too many derivations. Those were very overwhelming,
Oh,
and each will have like, okay, assume this. With that, can't keep anything in your head.
oh. So for yeah, so for these type of things, yeah, you don't need to remember all the derivation and all, but it's okay to have an idea of this.
Yeah.
Other- So okay, uh, so now we talk about okay. Now we saw what is overfitting, right?
Hmm.
Now let us discuss what is regularization. So why does overfitting happen? Overfitting happens because you are trying to memorize everything about the data. You are interested in learning everything about the data, and so you will not be able to generalize or say anything about some data that you have not seen before. So how to avoid overfitting? Because you don't want your models to remember everything. You want your models to be more generalizable. So there the concept of regularization comes in. So regularization basically says that suppose you have a set of features for some data, and you don't want your model to give much importance to all of to some features and less importance to others. You want your model to give, say, equal importance to almost all of the features. So there are various types of regularization. So I think here they talk about L2. Let me check. Give me a minute. Oh, these are a lot of slides. Hmm. Okay, so here they talk about L2 regularization. So there are various types of regularization. One is L1, L0, and this is L2 regularization. So L2 regularization basically says that you don't want your model to give high weightage to some features and low weightage to some features. That means suppose for a simple example, suppose I have some data point x, and suppose x has some d features, x1, x2, and xg. And now you say that, okay, suppose you train a model and it is overfitting, and it is overfitting because, say, it gives a very high weightage to x1, say w1 is high, w2 is high, and the rest of these are, say, small. So this is high, this is high, and rest of these are small. So suppose a new data point comes in for which this x1 or x2 features are
Excuse
small.
me, sir. Sorry to
Yeah.
interrupt. So we are assuming that the initial weights, what we have assigned is high. I mean high for say x1, x2.
Oh,
Is that the
I'm not.
assumption?
So x is my data point, and these are my features. And suppose we have learned the model. So these are my learned
Oh,
weights.
by
Suppose.
learning, after
Huh,
learning, it has found that
huh.
it is giving importance. Okay, okay, okay.
Yes, yes.
Yeah,
So
continue.
suppose my learned weights are such that it is giving very high importance to features x1 and x2, and it is giving very less importance to the rest of the features. And suppose a new data point comes along for which x1 and x2 are not that large, but suppose xd is large. So that means your model will not be able to give good result for the new data point. So what we want is that we don't want my points to have high importance for only some features. We want to give almost equal importance to all of the features. And by equal importance, I mean to all of the important features. Again, there will be some uh, redundant features. We don't talk about that. Suppose all of the features are important for now. And so how do we do that? So we can enforce this regularization by including a term in the loss function. So suppose uh, this is my parameter w, and suppose I say that my loss at w, or some modified loss at w, is the actual loss. So this may be your squared error or cross entropy or any other type of loss that you have seen. And then you say that, okay, let me add one more term to this. So we'll come to how this works. So now whenever we're talking about loss, what do we want? We want to minimize this, right? Minimize over some w. We want to minimize this loss. So that means we want to minimize this thing. So earlier we were only concerned about this part. This part was not there. So minimizing this, you can so we already know you can have some SGD or some back propagation. You can calculate the gradients in back propagation. You can use SGD to minimize this loss. But now that this extra term is there, what happens? Because we want to minimize this whole thing, right? So we want that this thing is small as well, because there is a plus sign here. So we want to minimize this as well as we want to minimize this. So what is w square, the this norm of w here? So this is basically your sum of the weights. So now if we want to minimize this, we want to minimize this. So that means we want to minimize all of this. So each of the individual weights will be minimized. So now this problem won't arise, right? That some weights will be very high, some weights will be very low. So because we are minimizing this whole thing instead of the loss, each of the weights will now ensure, this will ensure that none of the weights are very hard, very large. Each of the weights will be contained, each of the weights will be small. So that is how regularization helps. Now, one more important thing is this lambda. Yeah, one more important thing is lambda. Suppose I set lambda to be very high. Suppose this is say 100 or something. Suppose lambda is high. So if lambda is high, so that means if we want to minimize this w should be small, right? Because we want this to be small. So lambda high means it implies that this is small or smaller, you can say, because we're comparing. And if lambda is smaller, we can allow this to be a bit higher. So this regularization of this parameter lambda it controls how much the weights can or what the values of the weights can be. If lambda is very high, that means we are enforcing very strong regularization. That is, we are saying that I will not allow my weights to be very large. I will just I need very small values for the weights. And if lambda is small, then we can say that okay, I can allow for a bit w to be a bit large. So this is how this L2 regularization works. It just controls the values that your weights get, and this lambda is a hyperparameter. You have to give it as an input during whenever you are running the code. So if you are using PyTorch, if you use PyTorch, you may see something known as weight decay. So that weight decay is this L2 regularization part. So hope that is clear how pi and how L2 regularization works. So another thing they went to was I think that augmentation. Yeah, so data augmentation is basically uh, because say you're trying to learn an image or learn the image of a, let us say, car. So if you just look at the image of a car from one angle, and if you show the system a image of a car from a different angle, it won't be able to it won't be able to recognize, because it only knows that okay, my car looks like this from some angle. So that is why we come up with this technique called data augmentation. That is, given an image of a car, we perform some operations on the image. Say we rotate the car, we crop out some parts of the car, or we uh, basically, given an image of a car, we generate different types of images from the car, so that we say that okay, it does not memorize only one image of the car. It gets to know that okay, and even a rotated version of this is a car, or a cropped out version of this is a car, and so on. So that is how data augmentation works. So parameter sharing, okay, I think parameter sharing will be covered in CNNs. So any questions up to now? Yeah, so any other questions? So most of the methods that have been covered, yeah, the derivations may seem a bit involved, but uh, mostly it is about learning what techniques you can use, because whenever you're running a code, you may see that, yeah, you're getting a good training loss, even zero training loss, but your model is not learning. So that means you're overfitting, and then these techniques will come in handy. You can just do any of these regularization or data augmentation type of techniques, and probably it will work out for your case.
So for this L2 regularization, I mean, how it does not become zero? I mean, it becomes smaller, but it doesn't become zero.
Okay,
How is that possible?
yeah, that is a good question. So you cannot have zero, right? So if you have all of, because we are not only minimizing this part, we still have to minimize this part. We still have to minimize this loss. So if your W becomes zero, so that means this part will not be minimized. So because you have to minimize this whole part, this ensures that your W becomes small. This ensures that you cannot have very small W. You'll have some, at it will stop at some level of W, but it will not equate to zero. Because if it was only this part, yeah, setting W to zero is the minimum. But since this is here, we cannot have, the algorithm will not make W to be all zeros.
Okay. So this will retain features which are relevant only, right?
This will retain feature which are not relevant. You can say that this will give almost equal weightage to all of the features. It will not say that some features are more important and some features are less important. This will say that it will give almost equal weightage to each of the features that are there.
Okay. And that is taken care in L1. Is that the case?
So in L1, you can when we do L1 regularization, then some features will be given more importance and some features will be neglected, because then you, for L1, some weights will be zero and some weights will be non-zero. So there you will have which features are important. Then for them you will have weights to be non-zero, and for which features the way not that are not important, the weights will be set to zero. So that is L1 regularization. But for L2, you won't have zeros in the weights. You will have almost equal weightage to all of the features.
Got it. Thank you.
Yeah, if there are any questions for the autoencoders part, we can also discuss these, or for any other previous uh, lectures, we can also discuss those questions now.
One more question on this, like this dropout, is there any dependency on the dropout of this lambda value? How we should control the dropout in the network?
Oh, so dropout is a, so that is also a regularization technique, but that is not related to this. Uh, so in dropout, we, with some probability, we just drop some neurons out. You say that, okay, with some probability, this neuron is not going to be trained, but that is not exactly related to this L2 regularization, not that I'm aware of. So those are two different types of regularization techniques. So when we talk about dropout, we are actually talking about a type of ensemble learning, because you are training different models and combining the results of those different models. When we're talking about L2 regularization, we're just saying that I want my weights to be uh, to give equal importance to all of the features. So these are two different types of regularization techniques, uh,
Okay.
but this is not
But
related
there is a
to.
randomness now, means we cannot control like which neurons to drop and which neurons to keep.
Huh. For dropout, there is randomness, but here there is no randomness. That uh,
Okay.
because we want this quantity to be small. There is no randomness. We cannot say that we randomly make W1 small, we randomly make W2 small. We cannot say that. We are just saying that we want that our W1 W2 value should not be very large. But in dropout, there is randomness. We randomly drop some neuron. Uh, so those are two different things. Is that clear?
So this method is better as compared to dropout, or
So need not be. You just have to. Uh, I mean, you just have to check it out how which one works better. It depends from problem to problem.
okay, okay,
So there are a lot of techniques. You just have to try out which works best for your example.
okay, got it.
Yeah, if you have any more questions, we can discuss. I'll be here till 5. So